Yeah. So is the screen visible?
Yes, sir.
Okay. So today I am going to discuss how to model the cells or assembly of interconnected plates. So modeling of cells or assembly of interconnected plates. So what I am saying is essentially that let us say you have a cell like this, and you want to model this using flat elements. So those are known as facet elements. So then what you do is you know each element is going to be a flat element, although there is a possibility you can do the formulation in curvilinear coordinate system and your element can be a curved element, and then you use the strain displacement relations from cell theory involving curvature terms, radius of curvature terms, initial radius of curvature terms. But the other approach is to model this using the assembly of plate elements. So then you discretize this into a number of elements, flat elements. So then what you do is you discretize this using flat elements. So the discretization would be like, this will be flat, from here to here it would be flat, it would be flat. And so each portion is a flat portion. So you model it like this. So in this process, when you do, because each element, if you see, is in a different plane. So when we assemble, obviously we'll have to transform the element level governing equations to a common coordinate system. This is similar to now in the truss structures and frame structures, you have the members oriented in different directions. So first you transform the element level governing equation to a common coordinate system and then assemble them. So the same thing is needed here. Now another important thing is, like when we said, when I have talked about the plate elements, either the classical plate theory based elements or the Mendelian plate theory based elements, we have taken only W, theta x and theta y, assuming that there are only transverse loads, there were no in plane loads, and there is no coupling between bending and stretching. So we use those terms now. But here if you see, because the different elements are in different planes, so no, say the transverse displacement of one plate will cause in plane displacement, that is displacements of the middle surface along xy in the other element. So now for this case, we want to use the displacement field. So if you look at the displacement, so this I am still writing in the displacement field in local element coordinate system. So what I'm saying is, now suppose you have this element, so maybe you take this as x and this as y, this will be z. But for now this element, you see the orientation of the x is going to be different. No, this can be x, this would be y, and this would be z. Z would be normal to x and y plane, so that would be z. So the orientations are different. So first I am talking about the displacement field in the element local coordinate system. So now, as I said, because there is a different plate elements are in different planes, so bending displacement of one plate element will cause the in plane displacement of the middle surface in the other element. So we need to have the in plane displacements in the theory. So now let's say we are using the Mendelian plate theory for bending deformations. So we will have u, which is u naught function of xy plus z into theta x. Theta x is a function of xy. So earlier we had only this term. This was not there because I said there is only transverse load, and there's no coupling between the bending and mid plane stretching. So that this u naught term was not there, but now we have to include, because when plate elements are in different planes, due to coupling will cause the stretching of middle plane of the different elements, even though there is only load in the transverse direction normal to that is normal to each plate element. So then v will be similarly xyz will be equal to v naught xy and z into theta y, which is a function of x and y. And you remember this theta x is the rotation about positive y axis, and theta y is the rotation about negative x axis. So that's the convention we have used. And of course w, the transverse displacement, is assumed to be only function of x and y. So now we need to use these terms, and you keep in mind that these terms will also be needed when we are solving the problems involving large deformation, or if there is a bending stretching coupling. So the mid plane z equal to 0 plane has got in plane displacement, so then you have to include u naught and v naught. So particularly, for example, in composites, depending on the lamination scheme, there can be coupling between bending and stretching. So there also you need to include this u naught and v naught in the displacement field. And the steps are same, although rest of the steps for the development of the element level governing equations are same. So I will only just write here the important results, and the in between derivations you can do yourself. So now the strains would be epsilon xx would be del u naught by del x plus z into del theta x by del x. Epsilon y would be del v naught by del y. Earlier we had only z term, now we'll have this the del u naught by del x, del v naught by del y, these terms also. And gamma xy is del u naught by del y plus del v naught by del x plus z into del theta x by del y plus del theta y by del x. So that is in plane shear strain, and the transverse shear strains would be gamma xz would be del, it would be same what we had earlier, del w by del x plus theta x, and gamma yz would be del w by del y plus theta y. So these are the strains. And no, you can then talk of strain energy and the total potential energy functional. So I am writing the strain energy. So strain energy is you going to write as no, integration over half of integration over volume sigma transpose into epsilon plus tau transpose into gamma. So and then no, you do the explicit integration with respect to z. So finally you can write the strain energy as, strain energy pi can be written as, after the, I will explain you all the terms what are these. So you can write it as integration over area of the element, and then we have what is known as the membrane strain tensor into the extensional stiffness matrix A into the membrane strain tensor epsilon m dA. So this is known as the membrane strain energy, because this involves the strains due to u naught and v naught in plane displacements, plus the bending strain energy, so which is half of integration over area, and that is kappa transpose, this we have done earlier, so this term is same, into kappa dA. And then you have the transverse shear strain energy, so half integration over area, and then we have this gamma transpose into E matrix into gamma dA. So now this is the additional term. And now z equal to 0 surface is the middle surface. So in this there is no coupling between epsilon m and kappa. There is no coupling between extension and bending. So because no, the z equal to 0 is a middle surface, so z varies from minus h by 2 to plus h by 2, and the material properties are uniform through the thickness, so there is no coupling between epsilon m and kappa. So there is no coupling term here, as you see in this case. So now let me define the various quantities which are appearing here in the strain energy term. So where this epsilon m, which is the no membrane strain. So I am using this as del u naught by del x, del v naught by del y, and del u naught by del y plus del v naught by del x. This I am denoting as actually epsilon m, and we call this as membrane strains or membrane strain tensor. And then kappa you already know, so kappa is the same of what you already know, that is del theta x by del x, del theta y by del y, del theta x by del y plus del theta y by del x. So this we call as bending or curvature, bending strains or curvature tensor. And then you have gamma. So gamma is, we have defined this earlier, del w by del x plus theta x, del w by del y plus theta y, and this is transverse shear strains. And then you have these the AD and E matrices. So let me define those also. So A is going to be basically the integration of constitutive matrix through the thickness. So E by H 1 minus nu square, and so only H is coming. E upon 1 minus nu square into this matrix is already the constitutive matrix, as we have discussed earlier. So I am just writing the results. The derivation is similar to what we did earlier, and this in the literature is referred to as extensional stiffness coefficients matrix. And then D you already know, D is same, that is we have already derived that EH cube upon 12 1 minus nu square, and then 1 nu 0 nu 1 0 0 0 1 minus nu by 2. So this is bending stiffness coefficients matrix. And then E you already know, we have defined earlier. So we have this as EH into shear correction factor Ks divided by 2 into 1 plus nu 1001, and we call it as transverse shear stiffness coefficients matrix. Transverse shear stiffness coefficients matrix. So yeah, so this is what now you get as the strain energy. And now you can write the total potential energy functional, including the no for each element, including the uh, potential of transverse load and the boundary forces that we discussed earlier. Of course, you can also include the boundary forces along the n and t directions, normal and tangent direction. So the corresponding u naught n and u naught t will be coming in that. So those would be the additional thing. So I'm not writing that because the derivations are similar to what we have done earlier. So I want to highlight the important steps in this. So now when you formulate the element based on this, so let us say we want to formulate a four noded isoparametric element. So we will have say the arbitrary quadrilateral in uh, natural no physical coordinate space and a square in the natural coordinate space. So there is one to one mapping. So this is xi and eta. So now the degrees of freedom, if you look at each node, you are going to have the degrees of freedom as, let's say, first node. If you look at, so you will have u naught 1, v naught 1, and then w1, theta x1 and theta y1. Similarly, at node 2 you will have u naught 2, v naught 2, w2, theta x2 and theta y2. So similarly at 3 and 4, so you are going to have these degrees of freedom. Of course, so now if you look at the total for the element in the basically local, the coordinate system, you have these 5 degrees of freedom at each node. So for the elemental degrees of freedom will be 20, 5 into 4, 20 will be the elemental degrees of freedom. And the way we discussed already, the interpolation for the various field variables, say u naught will be equal to summation I going from 1 to 4 ni into u naught I, where u naught I is the value of u naught at ith node. Similarly, you will have v naught will be written as again summation I going from 1 to 4 ni into v naught I, and w would be equal to summation I going from 1 to 4 and I into wi. And so these are, no, now by now you know how to write these. So these are same I going from 1 to 4 and I theta xi, and theta y will be summation I going from 1 to 4 and I theta yi. So this will be the interpolation. And if you follow the steps we did earlier, now you can get the element level governing equation. So the form of, no, the you should try yourself to write the all the intermediate steps whatever I'm skipping over here, because this is similar, no, the standard approach to develop, write all the steps. So I'm not writing them. So finally, the when you, for an element in the local coordinate system, you will have element level governing equation. The form element level governing equation will be of the form, essentially, this ke d is equal to f external for the element plus f internal. And you can look at, the basically, the k will involve contribution from interpolation of epsilon m, interpolation of kappa, and interpolation of gamma. So it will involve contribution from all three. You will have, so for example, if you look at, let me write just ke. So ke would be, of course, finally you will evaluate the integration using a numerical integration, but let me write in terms of continuous integration. So -1 to +1, and then let us say bm is the the matrix involved relating the membrane strain and the corresponding degrees of freedom. So Bm transpose into A into Bm into determinant of J into d high d eta plus integration from -1, integration from -1, and let us say B is the matrix which relates the curvature and the vector of elemental degrees of freedom. So B transpose into D into B into J into d high into d eta, and plus integration from -1 to +1, -1 to +1, and you will have Bs transpose into E matrix into Bs into determinant of J into d high d eta. So you will obviously use, no, if you do the exact integration, you would use 2 by 2 integration for all the three stiffnesses, this one and this one. But if you use the, let's say, there could be no, you are using the same thing for thin problems, so then you may go for selective integration. So for this you might use 1 point integration, and these two you can use the 2 by 2 integration. There can be also a problem of actually membrane locking. So if you are doing the formulation in the curvilinear coordinate system, so in that case the membrane terms are also under integrated, but we are not doing that here. So no, if it is you may use the full integration for this term. So and reduce selecting one point integration for the transverse shear stiffness term. You will find that what is this b, so epsilon m is written as bm into DE. So the DE vector is going to be 20 by 1. At each node there are 5 degrees of freedom and 4 nodes, so it would be 20 by 1. So the matrix relating this epsilon m and D is your BM, and this you already know, the kappa is equal to matrix B into DE. So you know how to write BMB in terms of derivatives of the shape function. And similarly, the the strain gamma is equal to BS into D. So this is where these various terms are coming. And similarly, you can have the load vector. Now, main thing, as I talked at the beginning, that when you are using the different elements are having they are in different planes, so the local element coordinate system is different for each element. So before assembly, you will have to transform the element level governing equation. So that's the main thing actually I wanted to talk on this. So that is a transformation from element local coordinate system to global coordinate system. Transformation from local element uh, coordinate system to global coordinate system. That means we will have one common global coordinate system. So first we'll have to write the transform all the element level governing equation to a common global coordinate system and then assemble. So that is what would be needed. So now what I'm saying, first we need to define, because we want to express quantities with respect to local element coordinate system in terms of global coordinate system. So we need to know the unit vectors are the direction cosines of the local element coordinate system. So let me say that we have a global coordinate system, which is, let us say, we have x and the unit vector is I cap in this direction, and let us say we have capital Y and the unit vector is j cap in that direction, and let's say we have a capital Z and the unit vector is k cap. So this is the global coordinate system. Global coordinate system. And then you have element, a particular element, eth element. So for that eth element you have, say you have this x-axis, and it could be arbitrary quadrilateral. So y need not be aligned along this edge, but it can be at some angle. So that's y-axis, and then you have z-axis along the thickness. The unit vectors are, let's say, along x direction we have ex cap, along y direction we have ey cap, and along z direction we have ez cap. So these are the unit vectors. The nodes of the element are 1, 2, 3, and 4. So this is the element in the physical coordinate, local coordinate of the element. Now, when you do the discretization of the whole problem, so all the nodes, you would know the global xyz coordinates of all the nodes, in the discretization. So using the global coordinates of the various nodes of the element, we can write the unit vectors along x direction, unit vector along y direction, and unit vector along z direction. So let me first write the direction cosines of ex, that is local element coordinate axis. Direction cosines of ex cap. Ex cap is the unit vector along local element x axis. So let me denote the direction cosines by lm and n. So lx would be, as you know, the direction cosines would be, x axis is from node 1 to 2 of the element. So the x axis is defined along 1 to 2. So that is always along edge 1, 2. So this lx would be x2 minus x1 divided by length of the edge L12. So L12 is the length of the edge 12, and then mx would be as you know that y2 minus y1 divided by L12, and n x lmn are the direction cosines, and x means for the x-axis. So nx would be equal to z2 minus z1 upon L12. So as I said, no, the x, y, z are the xi, capital Xi, capital Yi, and capital Zi are the no, the coordinates of global coordinates of ith node. So that is how you are defining the direction cosine, and L12 is the length of edge 12. Then once we have defined ex, then another thing what we can do is we want to take the z axis normal to the plane of the element. So suppose if we take vector 1 2 and 1 3, either we can take vector 1 2 and 1 3, we can take vector 1 2 and vector 1 4, and then take the cross product of these two vectors, so we will get no, the unit vector along z direction. So let me write the yeah, hello, am I audible?
Yes, sir.
Hello. Okay.
Yes, sir.
Yes, sir.
Okay, okay. So now you see, similarly, no, as I said, we can write the direction cosines of Ez cap. So for that, I just said, no, you can take this Ez vector as vector from 1 to 2 cross vector from 1 to 3 divided by magnitude of vector 1 to 2 cross vector 1 to 3. So you know, this is, you can take no as your Ez cap, this vector, and the components of the vector Ez cap will be, let us say, Lz, Mz, and Nz. This small z I am using for the local z axis. Yeah, so I think let me write here the z as small z, so that I can differentiate between the small z and capital Z. So this is Z and this is Z axis. So here also this is small z. Yeah, that's the local element Z axis, and this is also small z. So now the components of this vector, when you do vector b12 cross b13 divided by magnitude of vector b12 cross b13, you will get the the components. So you will call those components as LZ, MZ, and NZ. So these will be the direction cosines of the unit vector along z axis. And once we have defined the unit vector along local element x axis and the unit vector along local element z axis, so then we can define the local no, unit vector along the local y coordinate. So before that, let me define these vectors, say b12. So the vector b12 is x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. And I have already told you that x1 y1 z1 x2 y2 z2 are the global xyz coordinates of node 1 and 2. So similarly, v vector v13, you would write it as x3 minus x1 into I cap plus y3 minus y1 into j cap and plus z3 minus z1 into k cap. So these are the unit vectors. No, these are the vectors v12 and v13. And once we have defined the vector Ez cap, so then
Hello,
we can
sir.
write the, yeah,
Sir, here, why don't we use V14?
yeah, we can use actually v14 also. Basically we require this element, each element to be in a same plane. So instead of v13, we can also use v14.
Okay.
Essentially we want two vector in the xy plane, so we can take any 13 or 14 also can be taken.
Okay.
Sometimes we also take the diagonals, so you can take 13 cross 2 4, that also you can do. So those, yeah, those are different possibilities. Then once we have defined the Ex cap and Ez cap, we can define the direction cosines of Ey cap. So Ey cap will be Ey cap, you can write as Ey cap as Ez cap cross Ex cap divided by magnitude of Ez cross Ex cap. Of course, Ez and Ex are the unit vectors, so you will actually get Ez cross Ex cap directly, because magnitude Ez cross Ex cap is going to be unity. And let us say the components of this vector are Ly, My, and Ny. So now once we have defined the unit vectors of no the unit vectors along element local x-axis, y-axis, and z-axis with respect to global coordinate system x, y, capital X, capital Y, and capital Z. So we can transform the various degrees of freedom from the local coordinate system to global coordinate system. So let me write that before. So let us say we have an element, and this is the element in the 1, 2, 3, and 4. So now we are going to do, what I am going to do is now if you look at the degrees of freedom, so one is that each node has degrees of freedom with respect to local coordinate axes. So for first node, that is u naught 1, v naught 1, w1, theta x1, and theta y1. And in the process, because we are going to assemble the different elements, so the xy rotation about x and y for other element might contribute to rotation about z. So we also introduce the rotation about z axis, although this will not come explicitly in the stiffness matrix or the load vector, but we are introducing here theta z1 also. So this is the these are the degrees of freedom with respect to local coordinate system. Now for the same node, we can have the degrees of freedom with respect to global coordinate system. So let us say the displacement with respect to global coordinate system are capital U1, capital V1, capital W1, and then the rotations are theta x1, capital X1, theta capital Y1, and theta capital Z1. So now unlike this, you can have for each node. So here you will see that these degrees of freedom are in the local coordinate system, and these degrees of freedom for the same node are in global coordinate system. So if you look at capital U1 is the displacement of node 1 along the capital X direction. B1 is the capital B1 is the displacement of node 1 along capital Y direction. Capital W1 is the displacement of node L1 along capital Z direction. And I'm using slightly a different notation for rotations in the global coordinate system. So let me say here, this theta x is the rotation about global x-axis, and of course at node 1. So this is if you look at this, theta x is the rotation about positive y-axis, that this theta small y1 is the rotation about negative x-axis at node 1. But for the global degrees of freedom, I am using this notation. So similarly, theta y1 is the rotation about global y-axis, and of course this is the rotation about global z-axis. And the theta x, the in the local coordinate system, as you remember, this is the rotation about small y-axis, and see, this is the rotation about negative x-axis.
Sir, but we have
And
not defined any theta z. like while taking the
Yeah, so
displacement.
we have not defined, but I'm introducing this. So, we don't, we have, this is theta z, small z is not appearing anywhere in the strain energy or the element coordinate system, but we introduce that additional degree of freedom. So when you define your, the B, and BS matrix, so you account for theta z also, although all the entries corresponding to theta z in that are going to be 0, but you introduce that so that when we assemble the elements in different planes, so we have consistency in the rotations. That is why we are introducing it. So this is the rotation about z axis.
Sir,
Yeah,
in the middle plate, we consider theta y equals to rotation about positive y axis.
yeah.
Eh,
In the first order theory, the way we have written the displacements, no. So theta small x is the rotation about positive y axis, and theta small y is the rotation about negative x axis. I had explained it earlier also when we started with Mendelian plate theory. That time I had explained you. So this clarity should be there, no, the difference between what I have in the local coordinate system and in the global coordinate system. Okay, are there any doubts in this? So
Sir,
now, yeah, yes, please.
previously we considered positive axis, and
I'm
here
I'm having a
saying
class. Come after. Yeah, yes, please.
previously you said positive y and x axis, but here you said
No, I didn't say earlier. Also, I have said theta x is the rotation about positive y axis, and theta y is the rotation about negative x axis. I have
oh,
very explicitly told that.
oh then I read wrong.
Yeah, yeah. So I have theta y. I said rotation about negative axis because why that is so? Because when you talk in terms of the the local the coordinate system and the element like this. So suppose if this is x y and this is y and this is z. So we have written the displacement along x direction as z into theta x. So if this is the normal, and then if it rotates about positive y axis like this, so then we get the displacement as z into theta x. So this rotation you see is the rotation about positive y axis. But when we look at this line, on the the edge having outward normal along the x-axis. So this is the normal to the middle surface, and for this we consider the rotation in this direction. That is the rotation like this. So then we get this displacement which is z into theta y, and that rotation if you see no, this rotation like this is the rotation about negative x-axis. So theta y is the rotation about negative x-axis. So I had explained this
Yes, sir.
no, yeah, that time. So now once you have this concept, and we have already defined the unit vectors along local element x-axis, y-axis, and z-axis. So we develop the element level governing equation in terms of the local element coordinate system, and then we want to write the the degrees of freedom in terms of local coordinate system, in terms of the global degrees of freedom with respect to global coordinate system. So you need to write, let's say for the ith node u naught I, v naught I, and wi, small wi. uh, so this is for the ith node, so subscript I is for the node. So you can project this the vector of displacement vector with respect to global coordinate axes is ui, vi, and wi. So see, the when we have this global displacement vector ui, vi, wi, its projection along unit vector along x-axis, that is along ex cap vector. If we take the dot product of ex cap and this displacement vector capital ui, capital vi, and wi, will get this displacement. So that dot product can be written as basically no your lx into ui mx into vy and nx into wi. So lx ui mx vi plus nx capital wi will give you this displacement ui. So similarly, if you take the projection of this vector capital ui capital vi capital wi along ey cap vector, you get this small v naught I. So that would be no ly my and ny. And then similarly, if you project this vector along ez cap, you get the small wi. So that would be lz mz and nz. So this is what you will get, and now you can write this. So you can say, let me denote this matrix by some matrix L, and then of course this vector remains as it is, ui vi and wi. So now what about the rotations? So we also have now this theta small xi, theta small yi, and theta small zi. So let me write this also. We want to write these in terms of rotations about global x-axis, y-axis and z-axis. So theta xi, theta yi and theta zi. Keep in mind theta x is the rotation about positive y-axis. So now, whereas this cap with respect to global system, this we have with respect to global x-axis, rotation about global x-axis, I have already explained you. This is about global y-axis, and this rotation about global z-axis. So when I want to write now theta xi, which is the rotation about y-axis, so I have to take the unit vector ey cap. So the dot product of, for small deformation, it would be the dot product of vector no ey cap and this vector. So that will give you here ly my and ny. And then theta y is actually the rotation about negative x-axis, whereas no, this theta xi capital theta yi theta capital zi, these are the rotations about positive xy and z axes, whereas this theta y is the rotation about negative x-axis. So we need to take ex cap and put a negative sign. So that would be minus lx minus mx and minus nx. And then theta z of course is the same, here also about local z axis, and this is about global z axis. So that you can write as the ez dot this vector theta capital xi theta capital y and theta capital zi. So that would be lz mz and nz. And let me write this no 3 by 3 matrix as lr into theta xi, theta yi and theta zi. And now see, what you need is the element level coordinate element level governing equation is actually in the local coordinate system. And now we want to write all the the entire vector of elemental degrees of freedom in the local coordinate system in terms of vector of elemental degrees of freedom in the global coordinate system. So what you have to do is, if you look at the vector of the elemental degrees of freedom in the local coordinate system, you will have u01 v01 w1 theta x1 theta y1 theta z1. Similarly for other nodes, so then you will have u02 v02 w2 theta x2 theta y2 theta z2 and so on. Lastly you will have no, for the last node, fourth node, theta z4, that would be the last element. In between we are going to put a full transformation matrix. So there is a full transformation matrix over here, and then you have here the global degrees of freedom. So first node you will have capital U1 capital V1 capital W1 theta capital X1 theta capital Y1 theta capital Z1. They will have U2 V2 W2 theta X2 theta Y2 theta Z2. and then you will have finally theta z4. So as you see, this is a vector of elemental degrees of freedom in the local coordinate system, and this is a vector of elemental degrees of freedom in the global coordinate system. So this is local coordinate system, and this is the global coordinate system. Global coordinate system. In between, you are going to have a transformation matrix. So now how do we have this transformation matrix? Is first, now if you look at the first three, these are the displacements u naught 1, v naught 1, and w1 of node 1 no in local coordinate system. So those can be written in terms of capital U1, capital V1, and capital W1. So we will get this L matrix which we have already defined, which would be a 3 by 3 matrix. And the other degrees of freedom will not contribute to small u naught 1, small v naught 1, and small w1. So you will put 0, and let's say put in the block of 3. So we will have basically now you are going to have 7 zeros null matrices. So 3, 4, 5, 6, and 7. So these all will be 3 by 3 null matrices. All will be 3 by 3 null matrices. Then next, if you look at this theta x1, theta y1, and theta z1, so those can be written in terms of these three. So you will write here first a null matrix which would be 3 by 3, and then you will bring in LR over here. LR is also 3 by 3, and then you will have the zero. All the zeros are 3 by 3. They are all 3 by 3. So no, essentially you can understand that all these have to be 3 by 3. So you will have to construct this matrix, this transformation matrix. Similarly, now if you look at these, so these will be written in terms of u2, v2, and w2. That is these three. So you will have here null matrix, and then L, and then remaining zeros. So now like that, no, you can construct the entire transformation matrix. You can construct this entire transformation matrix. So what you can actually do is you can write, let us say, small d is the vector of elemental degrees of freedom in the local coordinate system, which is actually this, is equal to a transformation matrix. So this I am calling as star t, and into this as de. This d is actually this vector which we have here, this vector. So this is how you can write the vector of degrees of freedom in the local element coordinate system in terms of the vector of elemental degree of freedom with respect to global coordinate system through this transformation matrix T. So as you know here, this small de is the vector of elemental degrees of freedom in local coordinate system, and capital DE is the vector of elemental degrees of freedom in global coordinate system, and T is the transformation matrix from local to global. So once you have this transformation matrix, you can convert the element level governing equation in local coordinate system into global coordinate system. So then now if you look at the element level coordinate element level governing equations, if you look at element level governing equation, so which is basically Ke into De is equal to F external for the element plus F internal. So in this, if you find, if you will see that no, the D is the we have already defined. So now D is equal to capital T into capital D. So we can write this as Ke into T into capital De is equal to, right hand side we will have F external for the element plus F internal for the element. In this, if you see the forces, whether we talk of the left hand side or the right hand side, are still in local coordinate system. So what we do is we pre-multiply above equation by T transpose, superscript T is for transpose, to express forces, whatever forces we have, whether K into capital T into D will also give you forces, and if external and internal are the forces, but they are with respect to global coordinate system. So we want to express them with respect to express forces with respect to global coordinate system, GCS. So now you can write finally this equation as T transpose into Ke into T into De is equal to T transpose into F external for the element plus T transpose into F internal for the element. Now this equation is in the global coordinate system. So this is the equation, element level governing equation in the global coordinate system. After this transformation, we can actually do the assembly. So essentially, let me write what I said. And when you look at this, there can be situation when all the elements are in the same plane. So then theta z, the all the stiffnesses corresponding to theta z would be 0. So the assembled, and after implementing the boundary condition, the stiffness matrix would still be singular. So you add a small value in the diagonal elements corresponding to theta z degrees of freedom. So and then you solve the problem. So that is how the entire thing is done. So I think let me complete this part and then I will stop. So now, as I said, no, the assembly is done after this transformation. So assembly is done. So you have to first transform the element level governing equations and then assemble into the global system. So assembly is done after transformation. And as I said, if all the elements are coplanar, then in the assembled stiffness matrix, if they are not coplanar, then you will have the contribution in theta z, but if they are coplanar, then you won't have. So if all the elements are coplanar, then in the assembled stiffness matrix, diagonal terms corresponding to theta z degrees of freedom will be 0, the diagonal elements. So this will make the stiffness matrix singular even after imposing the boundary condition.
Sir, then this situation will not be a cell element.
Yeah, then it is not a yeah, essentially it is a flat plate element, but no, ultimately you might end up using the same program, or the same element for either for all the elements coplanar or non-coplanar. So that is why I'm explaining this, that if you have this formulation you need to do this. Yeah, it will not be a cell element. Obviously it will not be a facet element in that case. So if we model a cell by this flat element, they are also referred to as facet elements, because they are flat elements, so they are also referred to as facet. So the theta z degrees of freedom will be 0, and this will make the, so will make this will make the stiffness matrix singular even after imposing the boundary conditions. If you don't impose a boundary condition, so for all cases the stiffness matrix is singular. But if the element is properly supported, so if you impose the, the structure is properly supported, then once you impose a boundary condition, the resulting reduced global stiffness matrix would be non-singular. But in this case, if the theta z diagonal elements are all 0, so this will make the stiffness matrix singular even after imposing the boundary conditions. So now how do we solve this problem? So to avoid this singularity, we add, let's say, one thousandth of the highest diagonal element in a non-zero diagonal element, we add, so we call that as small. So we add a small term in the diagonal entry in the stiffness matrix, in the diagonal entry in the stiffness matrix corresponding to theta z degrees of freedom. All you have to do that for all degrees of freedom. Yeah, so this is how you actually handle this type of problem. So I think this is where I want to stop. If you have any doubts and questions, you can ask.
Sir, can we like do like that? Like in boundary condition matrix, we also put theta z is equal to 0.
No, that you can do in the on the boundaries, but what about the intermediate nodes? So in the intermediate nodes also we'll have theta z as a degree of freedom, but the diagonal elements in the stiffness matrix corresponding to that degree of freedom would be 0. So that will make the stiffness matrix singular. So the boundary, you can boundary will not be a problem, but the non-boundary nodes where theta z is there as a degree of freedom, but there is no stiffness corresponding to that, so that will make the stiffness matrix singular. You will have the entire row and column corresponding to each theta z degree of freedom 0. So the stiffness matrix would be singular, and that is why you need to add these small terms. And usually that small term is taken as, let's say, 1,000th of diagonal elements corresponding to, say, theta x and theta y.
So like, can't we put a boundary condition on the internal nodes too, like in the
Yeah,
same manner as before?
okay. So if you are saying like that, yes, we can do that. So we can say that at all nodes theta z degree of freedom is 0, and if we and then eliminate those rows and columns, so yes, then we can solve the problem without adding that small term. But that's an additional task. If we don't want to do that, then we add a small element that does not influence the results actually. Yeah, we can
Okay,
do
sir.
that, what you are saying, definitely, yes.
So we are considering this small amount just for facet element, right?
Yeah, yeah.
For cell, there will be values.
Yeah, there
And
would be values because if the elements are in different planes, so then after the transformation, you will have some values corresponding to theta z stiffness terms.
but from the beginning we are considering only 5 degree of freedom.
Correct.
Uh,
We are
then
not
how,
considering. So when you write your all the H matrix, B matrix, and all those, so corresponding to theta z, you will always put zero in that. So now instead of 5 degrees of freedom at the element level, you will introduce this additional degree of freedom. So you will have 6 degrees of freedom at each node, and then accordingly you will define your basically BM matrix, B matrix, and BS matrix. So you'll have to update that. You need to make that change. Although I started with 5 degrees of freedom, but to account for theta z, no, although it will have zero contributions everywhere, but that has to be added in the nodal degrees of freedom and the elemental degree of freedom.
and another question is, sir, stiffness matrix will always be zero, is always be singular in every cases, in everywhere.
Yeah, if the assembled stiffness without any boundary conditions will always be singular. If you don't apply any boundary conditions, no, that is, if you don't eliminate any of the rows and columns corresponding to boundary condition, then it will always be singular. So if you have any number of element, you assemble them, the stiffness matrix would be singular. Or even you take a single element, its stiffness matrix would be singular.
So what about it is a multi-body system, then also singular.
No, multi-body system. Yeah, even if it is a multi-body system, then also it would be singular without imposing boundary condition. But now, if you are solving a dynamics problem, so in the dynamics problems, you will have mass matrix. So mass matrix is a non-singular. So then when you apply any time integration technique, so rather than inverting the stiffness matrix, you invert an effective matrix, which would be a combination of stiffness matrix and mass matrix. So that is a non-singular. So you can solve dynamics problems without any boundary conditions, but you cannot solve any statics problem without boundary conditions.
Okay, sir.
Sir,
Yeah.
sir, in order to submit the assignment one, there is no option to submit the coding file because in the data scope we have
No,
to submit on PDF.
you can convert that into a PDF, no, and then you have to upload a single PDF. So
For all
no,
the
your
program like
code.
4 and 5 program,
Pardon?
for the all 4 and 5 pages we have to convert it in PDF and merge them in a
PDF.
single PDF.
Yeah, yeah, right. And you have to upload the single PDF file.
But there are various subroutines, so we have to make PDF of
So
that as
yeah,
well.
yeah, you have to, yeah, all those subroutines would be part of the same PDF file.
Okay, sir.
You can also combine different PDFs, so that's also possible. You can convert individual subroutines into PDFs, different PDF files, and then you can combine. You can search in the Google PDF combine program, and then you can use that and convert into a single PDF and then upload that. Of course, take care of the sequence so when you are doing that.
Sir, what are the things we have to upload? Like only the coding part or
Yeah, if you know,
manual
either your
calculation also?
code should have all the explanations what you are doing, then just code and result is enough. But if your code does not have explanation, then you have to have the corresponding the formulations, uh, part of the formulation, say for example the shape functions, the B matrix, and those kind of things. Then you have to add as your notes. Or if you have in the code and code is annotated, then that is enough.
Okay. And sir, one more doubt. Like while evaluation, like will you consider the style of coding also? Like because I have not used subroutines, another thing. I have just written a one code.
Yeah,
In
so I
that
think that is fine. I'm not going to give any. No, I will not give any penalty to that. So don't worry about that.
okay, sir.
So anybody else? Any other question? Anybody?
Sir, one more question I had, like in the last step you did like pre-multiply equation by T transpose
Yeah,
to express with respect to global coordinate system.
yeah, forces with respect to
Yeah.
global coordinate system.
Yes, sir. But like initially when we had written this forces like F external, so it was
Yeah,
according to our small xyz.
right.
So
So
like
that will give you, when you look at the load vector, that will be basically with respect to small along say forces. If you look at, they will be along small x, y, and z axes.
okay. And sir, you told about like putting theta z I equal to 0. So my question was like capital theta zy will be present, right?
Yeah,
If
capital theta z. What I have done is to use the uniform formulation of the transformation matrix. In the local system also I have put theta small z.
yes,
And what I was saying is, if all the elements are in the same plane,
hmm,
so in that case the stiffness matrix after transformation, even after transformation, will not have any components corresponding to theta z degrees of freedom. So that is what I was referring to, that singularity, and then how to handle that.
yes, sir. I understood that part actually. Like
Yeah,
my
yeah,
doubt was actually whenever you are telling you're just telling theta zi, right? So I was
yeah,
confused. So we have not assumed like we have assumed that small theta zy is
yeah.
not present.
Yes.
So that's why finally, if we solve, for example, this shell problem also, finally
Yeah,
the boundary condition for theta small zi will be 0, right? But theta capital zi will be there because that is in the global coordinate, and according to global coordinate, there could be rotation of these uh, elements, like smaller elements we have.
yeah.
Okay,
No,
sir.
you in the, yeah, for different elements, if you see, there could be rotation small theta zi also, but there is no stiffness corresponding to that. Because when you have cell element, say, you have a complicated cell and you are modeling that using facet element, so even the small theta zi can have non-zero values, because after it's a transformation. So when you from the global, if you come to local, we have expressed local in terms of global, but if you come from global to local, you can have small theta zi also. If no, it's a cell structure or interconnected plates with in different planes.
Okay, sir.
Yeah,
So, sir,
yeah,
sir, why we are using different sign conventions for rotations in
yeah. We
local?
can actually use. Yeah, that's a right, very valid question. We could use the same sign convention. So if we use in the element formulation in the local coordinate system also, we can have theta x as rotation about x axis, theta y as rotation about y axis. So in that case, if you are using theta x as the rotation about y axis, positive y axis, and theta y as the rotation about positive y axis, so then you will write your u is equal to u naught plus z into theta y, and you will write v equal to v naught minus z into theta x. So and accordingly you have to do the other things as per that. So we can do actually that what you are saying. But another common, if you can mention, if you look at in the literature on these plate elements, usually in the local element coordinate system, theta x and theta y are taken rotations about positive y and negative x axis respectively. So that is why I followed that. But we can very well do that what you are saying. Yes.
Sir, then why don't we use the same in global also?
Yeah, global. See, when we are taking a global system, where, no, it is better to. I mean, for the interpretation point of view, it is better to have rotations about corresponding x, y, and z axes. So that is why that is used. Of course, that also the other way around also can be done, but I think the more appropriate way would be to use the local rotations also with respect to x and y axes, about x and y axes, and do the formulation.
Okay.
Yeah. Any other question? Okay, so if there are no questions, I'm stopping. Thank you all for your attention.
Sir, one more thing, sir.
Yeah,
Sir,
okay.
all the non-linear parts, whichever you are teaching us, like
Yeah.
we can refer J.N. Reddy also for this, right, sir? Because Asghar Bhatti was not present. So, are all this present in J.N. Reddy also?
Jane Reddy, that first book, which is an introduction to finite element method. So in that, most of the, I mean, some are not all of these, but some of these things you can find in that finite element method by Jane Reddy. Not the nonlinear book, but in the linear finite element method book, you can find some of these.
Okay, sir.
Yeah.
Sir, is there any PDF for Oscar Bhatti?
No, I don't have. Yeah. So any other question? So if there are no questions, I am stopping. Thank you all for your attention.
Thank you, sir.
Thank you.